How's everybody doing? Yes? Everybody's ready for lunch, right? All right, well, I'm going to take up the next hour while they finish preparing lunch. I do have to apologize to everybody. I wore a jacket today, probably misread the room, but I promise I actually know how to code, and we're going to be doing some, so don't judge me for the jacket. So a little bit about me. I started as a developer. I am now in business development and running our business, but I fill in the role of our CTO for improving, which means I get to play with a lot of really fun, kind of interesting things and figure out how to bring them to our business. And one of the biggest things that I found is that learning is one of my joys in life. So we're gonna get to do that together. I doubt I have all the answers to your questions, but I'm hoping you have cool questions that spend weekends in my future. So the first thing is, the AI and ML space is massively complex. There are a lot of moving parts, and there are people dumping hundreds of millions of dollars into R&D. At the end of this talk, you're not going to be one of those people unless you're already one of those people now. But you may be able to walk into the AI and ML space and understand where you can bring it into your day-to-day and approach a complex topic without it spending hours, days, weeks, months of your time learning linear algebra and picking up Python as a side hustle. All good? Awesome. I'm gonna need a little more interaction. I'm an extrovert. I'm making up for 2 years locked in a room. Oh, there we go. All right, pity laughter is appreciated. So when we talk about complexity, the AI and ML space is massively diverse. There are things that we've been doing in this space since the 70s. It's baked, it's boiled, and we don't even think about it as AI anymore. Anybody ever built something on top of a rules engine? Yes? Yes, hands? Awesome. So rules engines were expert systems. In the 70s, when we were building AI from its roots, we hit the first AI winter because we had to invent new math. Like, math hadn't gotten far enough for us to crunch some of the information we needed. And then we hit an AI winter around processing power because we exceeded the capacity of our Intel MMX chips. Oh, somebody's heard of it. I heard the joke. I heard the snicker. It's like, oh, I had one of those. And then we hit the we don't have enough data winter. Now, the good news is it's springtime. And I am certain there is another AI winter in our future. We just don't know where it's coming from. And so what we're going to be talking about is where you can carve off all that complexity on the things that have already been built but aren't really widely known. So you could literally go pull in a couple of NuGet package imports into your application tomorrow and just crank through building, training, and using models. We're going to build a few of them and code through that as a part of today. Now, that is not to say there's not difficulty in this, right? We talk about complexity. Something is either very simple, a limited number of parts that are easily understood, or complex, a lot of parts hard to understand. We have a lot of complexity in ML, but there are serious pieces of it where it's just easy because we do it a lot. Now, think about some of the decisions that systems make today. Do I make this loan or not? Do I invest in this property or not? Do I hire this person or not? Now, we've applied classification algorithms and clustering to all of these because we've gotten really, really good over the last 40 years of doing that. We put people in boxes. The boxes are funny shaped, but we've effectively put them in a box. We've gotten very good at that, and most business problems are about going, hey, here's the box we know about. Ooh, there's something outside of it. How do I deal with that? And it turns out that's really easy to do. You just got to think about the problem backwards, which for a developer, starting at, all right, I start at A, I go to B, I go to C, and I get to D. Makes sense. If I start backwards, I go, all right, I want to get to D. We'll let the computer figure out how to go from A to D. It might go backwards through the rest of the alphabet and go A, Z, Y, X, and I can't go any further because I'm not that smart. Pity, laughter, right here. There we go. All right, all right. But we don't care about the steps it takes as long as the outcome and the starting point are correct. And that just threw me for a mental loop. with AI. I was like, wait, I do care about the steps. I've built my entire career on knowing what those steps should be. And so we have to start thinking about it a little bit differently. This is the point where I go, this is not a marketing talk. AI is not changing the world. We're not all going to be unemployed in the next 10, well, AI is not changing the world any more than it already has. We're not all going to be unemployed in 10 years any more than we already were going to be. And hey, you could be replaced by a reasonably sophisticated Perl script is probably just as true as it was 10 years ago. We're not talking about like, oh yeah, this will make your day magically easier. What we're gonna aim for is, if you've ever seen this, this is the Gartner hype cycle, right? All new technology goes through this, and we all probably hear about it for the first time near that peak of inflated expectations, right? This is my favorite thing to show business people. I'm like, yeah. We need to be doing the AIs means you're at the peak of inflated expectations, right? It's like, we need business intelligence. I'm like, awesome, who are you hiring as your replacement? Pity laughter here. There we go. All right, see, the jokes don't get better, but you'll get used to them. So when we talk about the plateau of productivity, these are the places where the technology is pretty well baked. And given that we have massive processing power at our fingertips, we can do these with reasonably low cost, both in hardware and in effort, right? How many folks have an iPhone or an Android phone or a Google Pixel that was made in the last 5 years? The vast majority of the room, like completely expected result. Awesome. You have enough processing power to run the most complex AI model developed before 2010. The most complex AI models that were running on supercomputers can now be done on an iPad or an iPhone or an Android device. On-device video recognition and image recognition, we've got hardware to spare. So we're gonna stay out of the first half of this. If your question is, how do I write a model to do my job so that I can get another job and double my income without having to do more work? That talks down the hall. See, you guys are getting those cues for pity laughter perfectly. Thank you. All right. So we're gonna talk about intelligence because it's one of those things that everybody's like, oh yeah, AI. And then we have to start thinking about it, and it's like, there's actually a massive amount of different types of intelligence. We're gonna boil this down to, machine learning is using data to solve problems. That's it, right? Rather than using the people in this room to solve those problems by thinking through it and becoming experts in a domain, we're gonna make you do all that and use a bunch of data. Pity laughter. So you missed that cue, all right. So, data could literally be anything at this point. It could be images, it could be video, it could be GPS data. My favorite is GPS data. If you ever want to kind of dive into some of the weird things about how privacy doesn't exist anymore, talk about AI against GPS data. But the problems that we can solve are impressive. There's actually a startup that just closed its Series E funding and is going for FDA approval on a cell phone application that has over 90% accuracy identifying cancerous moles just by the image. So no more like going in once a year and going, what about this mole? What about this one? What about this one? You take a photo, the app highlights the problems and books the doctor's appointment for you for the biopsies. So you don't have to do those things. So like the convenience of those factors is getting incredibly cool. All of that because we have hundreds of millions of photos of moles. Now, AI and ML are used interchangeably. They're not, but I understand there's enough marketing people in the world, they're gonna get used interchangeably. Marketing people are the same ones that redefined megabyte to be 1,000 instead of 1,024 because it was easier. So AI is taking rules and data and giving you answers. Like, hey, here's the rules you're gonna obey, here's a new piece of data, predict its outcome. Is this mole cancerous? Is this flower a particular type of flower, right? That's the AI side of it. Machine learning is, I'm gonna take data and known answers, I'm gonna create new rules. Fairly simple and straightforward. It's when you combine these that they start cycling really, really, really quickly. At one point, the Google AI group that was reworking the indexer algorithm stopped understanding the rules that were being generated. So they shut it off until they could understand it. That was 13 years ago. We still don't understand it. Because it turns out this cycle can be done very, very, very rapidly by computers, way faster than human beings can crunch that amount of data. So we talk about intelligence. We're going to talk about those rules. Now, some of those rules include the capture of new data, right? And then, once we've captured data, we go, ooh, let me look at it, right? I look at grades, I look at the difficulty of the class to figure out if my kids are in trouble or if we take them out to dinner because they did really well, right? It's looking at that same piece of data from multiple perspectives. That's reasoning. And then you get into understanding, which is then creating results from that manipulated information. And then I go, all right, is that result valid? That's effectively trying to grasp what truth is as a computer. And then we go, all right, now there's relationships between all these conclusions. And this is pattern recognition. And this is something you do subconsciously. It's amazing. And it saved your life at least 10 times today. But we don't think about it, right? How many folks drove here? It saved your life at least 10 times today. But you don't think about it. Nobody thinks about, oh, that car up there and that car up there are differing ratios. I'm going to do the vector calculus to figure out which of the right lanes is to be in so that I don't have to hit the brakes on the wet roads, and I'm going to factor the coefficient of friction with water. If you do that, you're impressive to me. Like, I don't have that math brain to do that. Like, I stopped at calculus. But we don't do that. We've recognized patterns and we've learned it over time, and so we can do things like hit a fastball, which is doing a complex multivariable equation in a tenth of a second. I can't even read the question in a tenth of a second, but these guys that are hitting 98-mile-an-hour fastballs out of the park are doing that intuitively. And then we consider the meaning of those relationships. We actually attribute data mentally to the gaps between data points. The lack of data is data to us. And then we go, all right, what are facts that are measurable and validatable against the world, and what are my beliefs? The problem is, as human beings, we don't separate these. You treat your beliefs as if they're facts neurochemically. And so we have to teach computers to separate these, because facts are verifiable reality, and beliefs will get you blasted on Facebook. See, pity laughter, you're doing it, nice, right? And there's so many more. So when we talk about these, we're going to talk about what computers are good at. Now, this effectively boils down into these few places. Now, we're going to stay in the moderate to high space because that's where frameworks have been built for us to go do these things. And anything that's in the low to none space, avoid like the plague, because low to none means you're still in the R&D space. It means that we haven't truly built frameworks and algorithms and neural networks to understand and to operate these things. It also means massively expensive in time, money, effort, okay? Now, visual and spatial is image recognition, right? It's video recognition. We're getting better at this because we're capturing a ton of video. Anybody have a rough idea of how much video is generated daily on the planet? 50 terabytes. I heard 50 terabytes. Anybody above 50 terabytes? 50 terabytes. I got 50 terabytes. Bid going once. Huh? 5,000 terabytes. I got 5,000 terabytes up front. 14 petabytes a day. That is 0.41 yottabytes a year. 14 petabytes is bigger than the entirety of the internet in 2007. Daily. That's how much time we're spending on TikTok. But it also means we've got a massive amount of data available to parse through and capture. Like if you Google large video data sets, they're publicly available because of institutions and educational and universities. They've just made it available. I'm actually using a whole bunch of open source data sets to do this talk. And afterwards, I've gotten all the detail to Jared and the organizers and all that. The code base, all the data sets, follow-on learning, you're gonna get all of it. Like you'll go to the digital thing and it'll be there. Because if you wanna keep going, that's what we're hoping for. Now, body and kinesthetic is robotic control. It's the ability to move something through space and understand its interactions with the world around it. The Tesla factory uses a boatload of these. Now, it's incredibly expensive to move a machine with millimeter accuracy. But once you built the machine and trained it how to move around, it's actually really good at doing that very, very quickly. And is a better welder than like 97% of welders out there that are human beings. Now that means we're giving up the top 3% of human being potential, but it means we're raising the floor 97%. Right? There are still gonna be times where you need a human being to do it and you pay a lot for that specialist. But for the vast majority of times, a vertical bead weld in the middle of a Tesla Model S is fine for the 97%, right? Now, this breaks out for us into all the different service offerings. Now, I say ML Cloud, pick your provider. I haven't sold my soul to any of them. I've used GCP, I've used AWS, I've used some of the specialized clouds, I've used Azure. They all work just fine in the top half of this, right? Where we aim for developers, vision, speech, language, and the auto ML stuff, they all work just fine. Pick your poison, or my favorite version of this, whoever gives me the most free. Now, when you get into the platform side of it, right, you get into the stuff where you're having to tune it, measure it, model it, build it. That's the data science side of it. There's a few clouds that outperform, and it's the big three, right? Typically, the secondary providers are pretty crap unless they're a specialist cloud working on ML for data scientists. When you get into the bottom, build your own hardware. Like, on-prem is dead, except when you need a 50,000 GPU cluster. When it turns out when you're a significant purchaser of NVIDIA's total stock, you should probably own your own hardware. The full picture, here it is. We're gonna stay mainly in supervised learning, which is we know the answer before we train the model, okay? There's a whole bunch of unbounded things of like predicting weird human behavior. We're gonna stay out of that. We're gonna stay entirely on the supervised learning side of things. Most of what we're gonna be doing today is gonna be classification and regressions. So, unfortunately, most people misunderstand AI projects. 80% of the time and effort you're gonna spend on an AI and ML project is in data engineering. Our data is crap because it was created by human beings, and human beings don't care about typos. Computers care about typos. Oh, the image is blurry. Yeah, the computer's not gonna understand that image is blurry unless we tell it that image is blurry. It's gonna think that all people have fuzzy edges. And so we have to figure out a way to go through and do this. Now, we've gotten better at this, right? So let's say I need to do some analysis, and it's the 1980s. I'm gonna pick my 100 data points, if I'm really ambitious, 500 data points, and I'm gonna go create a graph that goes, all right, based on the risks on the account, kind of here's where we start losing customers. And that's an accurate representation of the data. But it's not precise because we could only use a certain amount of data because it was limited by the human being with a slide rule trying to put somebody on the moon, or whoever was in the sound stage in Hollywood, whatever your beliefs about the moon landing are. Oh, pity laughter, got it. Now, here's where we're at today. Topographical representation of complex data. And it goes, you know what? If I lay that arc on top of this, it's still accurate. It just doesn't tell the whole story. That means my data can lie to me. It also means my data can look really stupid. We're all expecting the T2000, and what we're getting is drunk Bender. It's like, what? So we tried to teach an AI model generationally, a machine learning model that we had back propagation, so it was an AI framework. We tried to teach it how to walk 300 meters over obstacles on 2 legs. The first answer that checked all the boxes was have 305-meter tall legs and fall over. It's like, oh, you got there, but no, you're still wrong. And so we had to start putting more and more and more constraints into the training model because the computer didn't know that its answer was stupid. It has no concept of stupid. That's why every time we put an AI bot out on the internet and it interacts with human beings, it becomes a racist idiot. It doesn't know that we're intentionally trying to break it, right? There are common mistruths in data that you have to protect for. Data engineering is where truth or falsehood is determined. Now, one of those is when we intentionally lie. Now, we were doing an actuarial analysis for automotive insurance, and we had to adjust for actual lying. When is a time when you get into an accident that you might lie on the police report? No, I haven't had anything to drink tonight. I wasn't on my cell phone. I was doing the speed limit. They ran the red light. My light was green. It wasn't yellow, just turned red, and I was speeding through it because I didn't care. And so we have these lies of commission where we intentionally, purposefully lie, but we consider them white lies, right? They're the little things, like filling out your weight on a healthcare form. I'm like, I'm 185, just like I was when I graduated high school. I'm 6'5". But then the computer needs to be able to adjust for these. My favorite one, and it's crazy important to this group, the average overstatement of salaries on salary surveys is 22%. That is the average that we lie up. So when somebody's like, yeah, I'm making 250, you're like, all right, adjust. All right, so like $1.80, right? Like, because there's a lot of social things that play into all those situations. Now, a mistruth of omission is when we just don't gather that data, right? And it's data that's probably important, like healthcare history forms asking about your family's history, mother's side, father's side, heart attack, stroke, mental illness. You know what question they don't ask on that form that's kind of important? Are you adopted? If I'm looking at genetic history, it's kind of an important question. Not on the form. Turns out, just adding that question increased the accuracy of predicting mental health issues and cardiac issues caused by genetics by over 14%. Because people were answering honestly, they just weren't asked the right questions. You're going to have to solve these. Now, mistruths of perspective, bias, and frame of reference are more insidious, right? The same automotive insurance carrier, we were looking at at-fault collisions as a significant indicator of increased premiums. And there were several states where the model broke. Anybody know why? Do what? No fault states, exactly. There are states who have passed a law that says every accident has no person at fault. Or they're largely referred to multi-fault states where everybody's at fault, right? But when I'm loading that data into a machine learning model and nobody's at fault, it lowers the premiums for everybody in that state. Whoops. Which, by the way, doesn't work well if you're running an insurance company. Works great if you're buying insurance, right? Mistruths of bias. This has been a huge conversation in loan approvals where race and gender bias are inherent in the data. And that's, keep in mind, I'm not talking about developers layering in their own opinions. I'm saying developers doing exactly the right things and asking all the right questions, but our historical data has bias in it because the people that generated the data had bias, right? If I look at home loans over the last 70 years in Chicago, I'm going to get a significant racial bias because there's been significant racial bias in home purchasing in Chicago. Not because I wrote the model wrong, but we have to correct for this because we're living in today, not 70 years ago Chicago. So I'm going to ask everybody to use your imagination for the rest of this because it's actually very, very, very simple to build some cool things. So I'm going to switch over to code and stop talking, and everybody's like, oh, thank God. So as soon as I find my clicker, there we go. All right. Here we go. All right. So anybody in here garden? Like, oh, wow, yes. All right. I asked that question in Texas, and everybody's like, what do you mean? I'm from Houston, by the way. I flew up for visiting friends and here with you guys. And yeah, I don't get gardeners a lot in conferences in Texas. So one of the interesting data problems is genetic identification of irises. So the flower, the iris. Genetic identification, there are 3 types of iris. And the way you identify them is either incredibly expensive genetic testing or the length and width of the flower petal and the length and the width of the leaf. And so if we enter all that data into an open data set, which thankfully a university did because they were trying to teach AI to a bunch of undergrads, we get a very easily usable model. Now, in this model, I have exactly 0 Python. I have exactly 0 math skills, okay? So the first thing we're going to be doing is loading our data. I go and I get it out of a file. Now, this is the code base that you're going to get access to after this. And you'll notice that I've embedded the test data, the training data, and the full data set. You can tell it's very well-prepared data. It's a CSV, that's it. So not overly complex. Any CSV loader, parser, whatever you want to use, have after it. In this case, I just use the ones baked into ML.NET. Now, if you're like, well, I don't code in .NET, I'm a Java person. Awesome. Deep learning for J, the incog framework, Spring MLlib, all do the same thing. Because we're building frameworks to try and make machine learning easily accessible to a common developer. So I'm going to include links to downloading and getting started with all those things. Feel free. Like, I switch between Java and .NET often. When I'm super terrified, I code in Haskell. So feel free to pick your poison. Oh, I heard a snicker. Somebody's actually done discrete math in Haskell. Yes, we can talk after. So I load up my training data, my test data, and the full data set. They're exactly the same parser. It's just load from text file. And then once I've gotten my test data, I'm going to set up and train my model. Now, before I open this up, you're about to get attacked by a wild pack of jargon. Now, it's important when facing a pack of jargon to nod your head like you understand and speak confidently, and the jargon will go away, okay? All right. So the first thing we're going to do is we're going to map our key column. Now, our key column is the answer. That's it. It's what kind of iris that row is. In our data set, it's 0, 1, or 2, because 0-based is the right answer. I don't care what you code in, it's the right answer. Which is why the US international extension should just be +0. Not +1, +0. I'm getting thumbs up, I love you guys. All right, so, and then we're going to plug in all the features. That is the things that matter. You notice the length, the width of the sepal, that is the leaf, and the length and the width of the petal. And we're going to smash all that together. Because I actually don't care about it being a number. Remember I said we're gonna get from A to D without caring about the steps? The computer doesn't care that that's a number at all. It's going to vectorize it, which is a fancy way of saying it's going to use a hashing algorithm to create a number that represents that unique string. It's not gonna use the numbers anyway. So I don't care that they're numbers. I can literally just smash them all together, treat them like strings. It's like JavaScript. Types don't matter. Hey, JavaScript developers, nice. All right, and then I'm gonna train it. And I'm gonna go, all right, SDCA maximum entropy. Everybody knows, awesome, let's moving on. All right, so it's a coordinate descent regression, which effectively just, there's some built-in ones. In this case, it's using a stochastic descent. If you want, go look it up. If you don't, just memorize that. However, there are some significant other ones. Naive Bayes, the maximum entropy is basically going, all right, I'm gonna configure it for max entropy so that features fall off very quickly versus a slow degrading of how important they are. Because if we figure out that the leaf width doesn't matter at all, we wanna figure that out quickly. That's it. And then you have non-calibrated. It's like, my data's random, figure it out. But in this case, maximum entropy is the one I'm gonna use for right now. We're actually gonna end having the computer figure it all out for us because I'm not that smart. And then we go, all right, once you get a prediction, match it to the key column. That's it. And then train the model. Now, our data set in this case has about 4,500 records, so it's not a huge number of records. Training a model takes a lot of time, and the time is typically linear to the amount of data you're training with. How long do you think this takes to train for 4,500 records in 2010? In 2010. I heard 2 seconds. Couple of days. So in our case, we're gonna go right over here. And by the way, I'm using Rider. Use the IDE of your choice. However, I have to, before I say anything else, say I'm not in any way compensated by JetBrains or affiliated with them in any way. I buy their tools. If JetBrains makes an IDE for your language, it's the right IDE for your language. So, if JetBrains is sponsoring, you're welcome. If not, come on, support SurTrek next year. All right. So, I'm gonna go out and I'm gonna train my model, and it's in the console output at the bottom. I guess I could make that bigger for everybody. And it went through and it trained the model. It's done, and then it evaluated the model. So we're gonna look at some of these evaluations. So the first thing you find is that our Sentosa and Virginica, which are the 2 most common types of iris, it's very, very, very good at predicting. 99.98% accuracy on the Sentosa, 99.99% accuracy on the Virginica. And then we get to the versicolor, and it's wrong. Now it's possibly wrong because I chose the wrong algorithm. It's possibly wrong because I need more data, right? And that's where we get to kind of play around with it. But that's it. Literally, those 17 lines of code and running it, we have built and trained a model against the data set. That's it. Super chill and easy. Now, imagine that this is trying to find outliers in error logs that are already text-based on a server. What's our most common errors? What are our outlier areas? I can parse that, load it in, featureize it, and go, yeah, categorize this error as most likely to crash the server. Which, by the way, wicked fun when we built this model with HP. Terrifying that they know 4 or 5 days ahead of a server crash that it's on its way to crashing. Workload predictions on whether I'm gonna overload memory and CPU and the convergence of things. There's all sorts of cool little things that you can go discover. And that is translating data to information. It's not providing any insight yet, because then you have to figure out what you're gonna do with it, right? Machine learning models live in the middle of an application. They don't have a UI. I'm running them in a console lab. Then you got to figure out how to plug that into your decision-making system. In no way should you just have the computer go make decisions that interact with the real world unless you're very, very good with this. But giving advice to a user is incredibly powerful. Like, hey, we've already looked at this. Here's likely the problem. Might save them 2 hours of analysis. Questions. Going to give you an opportunity to wake up. Awesome. So what I'm going to need you to do is manually factor a stochastic descent for 4,500. No, I'm kidding. That'll be in the homework. All right. So when I said use your imagination, the first step is identifying the problem space that ML works well with. You've just seen that, okay, I could probably spend half an hour and build a model. Where could I go do this? Side hustle, real work, whatever. Now, the common elements of almost everything that AI is good at today, and it's cheap and it's easy to build today, is it's a very specific task, it's time intensive, and that a human being has to currently do it. Automating something a computer does today, why bother? Like, it does it today. You might make it faster, but like, let's save human beings time, right? Let's let them get out and get into gardening, apparently. The benefit is typically human when we talk about the value. So when you're looking at places to apply this, look at human value, right? Who loves reading LinkedIn? Like you're like, oh yeah, LinkedIn's my jam. I fall into a scroll hole every day. I love LinkedIn. However, I wrote a visual parser for LinkedIn to identify posts that are important versus posts that are filler. Because no matter how long I scroll, I never reach the end of the internet. Like, I never get to the end and LinkedIn's like, look, you're totally good. You don't need to be on our platform anymore. Like, you've read everything. We're refeeding you the same post from an hour ago because you're never going to notice. You can go on with the rest of your day. So I wrote a visual parser plugin for Chrome to do that. And it saves me so much time. It auto-scrolls to the posts that matter. It's like, oh yeah. And then it puts a little box around it. Green box, really important. Yellow box, maybe. No box, skip it. All of this to save me time. I stay caught up with all my friends' careers and congrats and new position, promoted, awesome, in way less time than I actually used to because the scroll hole was deep. I don't know what those things are for you. For me, LinkedIn's a big part of my job because I'm in sales. Oh, sorry. I used to be a developer, I swear. But it was time consuming to try and stay connected with everybody. And I believe that if I wrote the system that shows you I care about you, that should count. Like I wrote a reminder to randomly tell me to go buy flowers for my wife. It doesn't make the flowers any less real. But it gives us the superhuman version of it. I also have started layering in sentiment analysis. Like, ooh, reach out to them. Their post, it's positive in content, but their word selection, sentence structure, and tone, something's wrong. See how they're doing. And I run it across our Teams interactions that I have via chat. And I'm like, ping somebody, be like, hey, you okay? Never have they come back and gone, yep, totally good. It's always like, thanks for asking. And then you gotta, deal with all the human things. But the big part of this is being able to take advantage of it. Now, we're gonna dive super deep into terminology, super deep, all right? So stop me if you feel attacked by jargon. If you nod and look confident, I'm gonna keep going. Okay. So, Oftentimes, people talk about AI and ML, and they want to sound smart. They want you to be like, oh yeah, I'm giving that talk about AI and ML later today, like 11 o'clock and 17, just so that you're like, holy crap, that dude's smart. I'm like, yeah, jack it. We're going to take away all that power from them, including from me, right? So you've heard neural network. Neural network is a description of decision-making nodes, right? Hey, how long is that pedal is a simple question, right? That's a node in a neural network. That's it. It's a simple question and an answer. The answer goes on down the line. We've done this with distributed systems since the dawn of WebSphere and BizTalk. This is not new. We just gave it a new name so we could sound important. And there's some difference to how it interacts, but not much. So we're going to start with a simple neural network, right? We have factors or features, things that matter. That's all it means. This matters. By the way, you don't feed in things that don't matter. The rest of the world calls this data. But that doesn't sound impressive, so they're factors. It sounds mathy. And then we have outputs or predictions. It's answers. Like, come on, y'all. Let's boil this back down. We have weights between those. How important is this? It turns out that pedal width matters a lot, and leaf width doesn't matter much at all. So we put more weight on pedal width than we do on leaf width. How important is it? That's all that is, right? And then bias. If I know that you're overstating salary on my salary survey that I sent out, I can adjust that before I analyze it. That is literally called putting a bias into a model, which if you ever publish a paper and you're like, here are the biases we put into our model, you're getting blasted on LinkedIn. But if you ever want to read some fun white papers, go look at some of those. Like they're adjusting for some really wicked problems. And then we have observations. Things happened. That's it. They were the things that went in and the things that came out. Like, it's like when my youngest son is 9 now, but when he was 3, it's like, Daddy, I went potty. I'm like, I didn't need that observation. Got it. Training data is the data we use to build the rules. That's it. Testing data is the data we use to test the rules, right? You'll hear a ratio thrown around, like, oh yeah, we were 4-to-1 on that test. That is, we trained with 4 pieces of data, tested with 1, right? 5-to-1 is 5-to-1, 5 points of data in training for every point in testing. That's it. Back propagation. We took our outputs and ran them back through to try and make it better. That's it. Any questions? That's a simple network. That's all the jargon. Feel free to be less impressed with me. I'll tell you what, I'll take the jacket off now that we've gotten the jargon out of the way. All right. I'm less intelligent after those slides, right? Okay, any questions on the jargon? I'm looking into a spotlight. If you're raising your hand, I'm toast, so shout.
So if you have a database or a database, how would you save testing data versus training?
So here's the fun thing. I wouldn't. I'd train on everything. Because then you can what's called fold, where you train with the first third, let's say we break 100,000 records into 5 pieces, equal sizes, right? I take the first 80,000 records and train and test with the last 20. And then I do that 5 times, testing with a different 20K each time, and then I figure out which combination was the most accurate, and I use that one. It's called folding. But effectively, every piece gets trained and tested. It's a little more processor intense, but I would say don't separate them unless you've got hundreds of millions of records.
So do you typically start with the same weight for all the variables and then let it fix itself?
So yes, unless I know And no is a dangerous word in the ML space. Unless I know that starting with a different weight gives me a different outcome, right? Like if I start with perfectly equal weights, the system itself might not learn fast enough to devalue leaf weight. And my test data may be skewed by it. So if, like, the science of botany has said that leaf is the least important measure, I'm like, okay, if I adjust the weights to start, I can train faster with less records and get better accuracy. And so I typically will start perfectly even if I'm not an expert in the domain. However, there are some systems where you should start with weights attached to them. Like if I'm doing financial prediction, profitability gets weighted from the start. Like, it turns out no model matters unless we make money. That's where you start layering in some assumptions, but keep in mind, every assumption you layer in becomes dangerous. Great questions. All right. Sure. So I typically view training a model as an iterative process. And so I'll go through and I'll run like a very naive training to give me a baseline. And then I'll go back through and layer in information and change them. I'll actually add factors and those kind of things to figure out if it mattered or not. Because I'm not a data scientist. Now, when I talk to my data scientist friends, they tell me that's really stupid and inefficient to spend 3 weeks testing a ton of variations when they could spend 3 weeks doing the math and have the right one automatically. I'm like, but we both spent 3 weeks. So, yes, you could do a lot of deeper analysis. I typically just evaluate accuracy and iterate. But I'm not a mathlete. Like, I tried, I injured myself. Like, yeah, I pulled my Pythagoras. All right. So, we get into more complex networks. This is how we do bigger and better things. Like when we do neural linguistics, when we do natural language analysis, we tear apart a sentence to the words, right? But does of, or and, or the have importance in a sentence? Not by themselves. And so we actually have to break it apart into chunks, and we have to do a bunch more complex things like, I'm going to take every word, but then for certain words, I'm going to take the words around them. And so we have to do a lot more of those things. Currently, the most advanced natural language processing system on the planet has 3 trillion nodes. Yeah. Well, sorry. The most advanced human-created one. Well, that's still a bad misnomer because human beings are human-created. The only no, that's a bad misnomer too. The computer one has 3 trillion. We have several hundred billion. And we're better at it because it turns out ours can connect randomly and at will. So layers is how we talk about the complexity of a model, right? More layers, more complexity, more problems. You have your input layer, which is where everything comes in, right? Now you can introduce in later layers new input. It's just not the input layer, right? Because you're adding that variable later when it actually matters, rather than being a factor on the way in. All your factors come in the input layer, most of the time. You have hidden layers, that is, they don't talk to the world. They don't make decisions, they don't make predictions, and they don't talk to input layers, or they don't talk to inputs. They're all your middle processors, right? Like, these are the queues and processors that you've got on your Kafka data stream or your BizTalk combinations or your distributed network. Like, you've got a service processor that no human being ever interacts with. That's your hidden layer. And then you got your outputs. Your outputs make predictions just like the earlier ones. Hyperparameters come into this. Now, hyperparameters are the configuration of the system, right? How much do I weight this layer over that layer? Do I backpropagate? Do I control the behavior and function so that I go, all right, for it to come from node 1 to node 3 on the next layer, it has to pass this check. That's a hyperparameter. And then model structure lays out nodes and layers, and this is how technologists in the data space compare how smart they are. It's like, oh, you're only working on an 18-layer system? I cranked out a 24-layer system last week. Right? It's like lines of code for data scientists. It's awesome. It's like, yeah, our system's got 15 million lines of code. It's like, that sounds horrible. You write in JavaScript, don't you? Sorry, I'm being mean to JavaScript because it's terrible. But I should also include every other language ever because they all have their perks. But yeah, model structure, number of layers largely outside of the operations and platform side of space doesn't matter. When I say doesn't matter, it's like how much RAM your SQL server is using. It's not something you actually care about until it becomes a problem. Make sense? Okay. And then lastly is the division of data. This is the testing to training. If you use folding, your division to data literally doesn't matter. And model development. So if you were to go do this tomorrow, which I'm hoping you do, like take a Saturday, figure out like when the best, time to plant your irises are. By the way, you'll need eye drops afterwards. There we go, yeah. So, model development looks identical regardless of what you're doing. Doesn't matter whether you're building something to automatically manage a rover on Mars, or you're trying to identify the right type of botany. You gather your data and you prepare it. Remember I said 80% of the effort is in those first two steps, right? Like, you're gonna spend a lot of time with a CSV. Like, you're like, Excel, I love you. Mac version of Excel, I hate you because column index lookup doesn't work. And then you're gonna train your model, you're gonna test it, and you're gonna go, how good was it? And then at the end of it, you're gonna go, wow, that was crappy, I'm gonna try again. And you're gonna keep working through that and making it more accurate, right? This is simply the iterative approach, I'll use the buzzword, it's the agile approach, because that's not what agile means, to go through and develop something. And then you save that, and you use it over and over and over again, and never have to train it again until the world changes. Like, until you find an error in its accuracy, until you want to reevaluate it because you have more data, whatever, you train models one time, and you put them in production, and they run for a very, very long time in over 70% of the use cases for machine learning. Back propagation is not a requirement. Like, everybody's like, well, I gotta get a model, and then I gotta feed its answers backwards so it's constantly learning. I'm like, no, to flip hamburgers, you do not need the T2000. Drunk Bender works fine. As long as you're okay with a little beer bottle glass in your burger, it's fine. But yeah, most of the time we're not needing of a lot of the advanced topics that we talk about in the R&D space for AI and ML. But those topics get really cool titles and clickbait on LinkedIn, and so it drives this perception that we need to be there. Now, if you want to do this really well, I'm going to switch back over to code. There's some great tools that take everything I just told you and does it for you, right? Like, it's the Martha Stewart cookies version. Like, you put them in, and then you pull out the baked ones. You're like, wait, the oven cooked them instantly? So AutoML is my favorite version of this. So AutoML, I load the data, I tell it that I'm trying to classify things, and then go, figure out the right algorithm, please. And you know what it does? It brute forces it. It runs all the algorithms and goes, oh, this one was the most accurate. Which, well, apparently I'm going to be debugging that instead of running it. And so we're going to run it for 60 seconds. And while this does some work, we're going to talk. It literally takes all of the standard built algorithms for classification and then runs them all and goes, here's the most accurate, I've saved it for you to use later. When I said that you could get started with very little effort tomorrow, this is where I was pointing you. By the way, there's actually an online version where you just drop your CSV and it auto parses it and runs the AIML for you. Like, it's absurd how simple we've made the entry point. But it's something nobody talks about. Massive amounts of business value, and you ever want to look really impressive, tell your product owner on Monday, you're like, yeah, on Saturday I cranked out a model. I think I can increase the conversion rate on our e-com site by about 6%. Like, you're promoted. It sounds way more impressive than it actually is. And the good news is, we can totally take advantage of this. As long as I'm not actually paused. I'm not. All right, tell you what, we're actually going to run that because the debugger's going to get really mad at it. So, any questions? Well, hey, there it goes. Debuggers slow things down. If you want to train a model from scratch, pick your data set. And it wouldn't be a demo until something broke. So you have this data. You have it in the applications you work with. Anybody writing an application that has no data? It doesn't read any data in, it doesn't store any data, it doesn't produce any data? Okay. You have this, right? Whether it's loan information, whether it's insurance information, whether it's financials, whether it's healthcare, whether it's e-com, doesn't matter. You have data. And so if you take that and you go, all right, what's a data set where we often make decisions, but it takes complex crunching of data? Give you my favorite example. We took the geophysics data of drilling in real time. Now, a drilling engineer, when you're poking a hole in the world, is a fairly important job, but it takes days for them to go through and crunch and analyze a bunch of information to figure out you made a mistake 3 days ago. And now you have to create a new plan to fix it because your problem is 4,000 feet below you. What if that happened in real time? And you could actually stop, correct it, and move on. That question drove us to working with one of our clients to create a real-time drilling analysis system that created $1.7 billion of saved cost. It took 9 weeks. We had all the data. There was a person with an Excel spreadsheet doing this work. So you want to find the best places to apply this at your office? Find the person with the most complex spreadsheet you can find. Like, they're probably in accounting. They're probably in accounting. But like, find the person you're like, hey, how do you do factorization and sums when you've got multiple columns to multiply? And they're like, oh, here's the function. That's your person. Like, become her best friend, sit down and be like, all right, what's your most complex drilling scheduling, maintenance and parts prediction? Like, there's probably an inventory person somewhere with a 44-tab spreadsheet where all the tabs talk to each other, and there's macros in it and all that. And they're the people that you can make their lives way better by simply providing all the analysis and going, here's your stuff, so that they can make decisions. But once you've got the problem space, you've also got the data when it comes to business. Very rarely do we run into the place where we just don't have data. We might not have enough, that's a different conversation, but you likely already have this. Whether it's in a SQL database or Mongo or Raven or Cassandra or whatever, doesn't matter. This thing's gonna eat it anyway. Answer your question, I hope? Okay. Oh, all right, so this thing bailed out. You'll notice that it ran our stochastic descent. It also ran a perceptron, and then it ran a GMB multi, or a GBM multi. And it turns out that I should probably be using a light GMB, or GBM. Awesome, so I'm gonna use that one next. I don't actually have to learn the linear algebra to go do that. Now, is it valuable to you? Yes. But it's a lot like understanding threading is valuable in C# and Java, but you don't learn it on day one. And some people have entirely successful careers without ever learning it. Now, because we have glazed over a ton of complex topics, and I'm running out of time. Nick's giving me like the, hey, I'm gonna try and help. So, we're actually teaching the 2-day version where every lab I just talked about, we actually build and dive into the algorithms. And so if you would like, I talked our training team into creating this just for the people here. Don't share it. And you can get into that class, have after it. This is happening with or without you. It'd be kind of cool to know, it was with you. And then I'm gonna stick around for any questions. My timer just went off. So hopefully you find value in that. If you look at this and you go, dude, I can't afford $500, come talk to me and we'll figure out a way to make that happen. Hopefully valuable. Okay.